Hello there. This is Dr. Maxwell again, and today we're going to talk about section 3.2. And maybe you've read this in your book, or maybe you wanted to wait till after the lecture to read it. Either way. But what we're going to do in this section is compare the sizes of infinite sets. And our only tool basically to compare infinite sets are one-to-one correspondences. Now, in section 3.1, we learned about one-to-one correspondences and what the cardinality of a set is. And we talked about how if two sets have the same cardinality, then you can create a one-to-one correspondence between them. And this is some useful notation that we need to understand. If I put the set A inside these bars that looks like an absolute value sign, this means the cardinality of the set A. And when I write equals between two sets like this, it means A and B have the same cardinality. So, one question that we are going to answer, among others today, is how much bigger is the set of rational numbers? We use this symbol Q. Remember that came from the word quotient. How much bigger is that set than the set of natural numbers? Gets this N symbol. Now, you may or may not recall from the Hotel Infinity that we have a name for the cardinality of the natural numbers. That's called Aleph Null. Aleph is the first letter of the Greek alphabet. Null just means zero. Okay, so we're going to be comparing the cardinality of the natural numbers to the cardinality of the rational numbers. And your instinct is probably that the rational numbers are much bigger. That's a much bigger set because we've already talked about this. How many fractions are there between 0 and 1? How many rational numbers between 0 and 1? Well, there are infinitely many. And here is an example. This list goes on forever, but that never reaches 0. So we already have a feel for these rational numbers, that there's so many more rational numbers than there are natural numbers. But before we get there, let's make sure we understand cardinality. We can think of it as the number of things in a set. And again, two sets have the same cardinality if you can form a one-to-one correspondence between the elements of one set and the elements of another. Now this picture represents two sets. On the left-hand side here we have the set of stars on this flag. And over here we have the set of states in the USA. Now I think that we know that the number of stars on the flag is the same as the number of states, so I can write this. These two have the same cardinality. There's one star for each state, and each state represents one star. Okay, so our first task is we will compare the set of natural numbers to a different set, which is a set of natural numbers, but we took away the number 1. So here are the natural numbers, and here are the natural numbers without the number 1. And there's a question. Which set is larger? Well, we did take something away from this set. So maybe you think that this is larger. Well, our only tool is a one-to-one correspondence. And this is how we'll get started with a one-to-one correspondence. We make a table. We're going to list the elements in each set. If we can pair them up in such a way that we are convinced that there is a one-to-one correspondence between these two sets, then we will know which set is bigger or they're equal. So I'm going to pair the number 1 with 2, the number 2 with 3, and so on. The number 8 gets paired with the number 9. So in general, if I'm looking at some natural number n, do you see what its partner would be over here in this set? Isn't that n plus 1? So this is a perfectly good one-to-one correspondence. I have shown that these two sets are equal. They both have cardinality aleph null. Every number in this set corresponds to exactly one number in this set and vice versa. So this is interesting. We removed one number from the natural numbers, but it did not change its size. So you can take away a number and it doesn't change the cardinality or the size. Okay, so let's keep going. Let's talk about another set. What about the even natural numbers, which I give the letter E, and the natural numbers, which get the letter N? Now, I would think that there's only half as many. Is this a smaller set? It certainly seems like it would be. In order to compare the sizes of infinite sets, we need to try to form a one-to-one correspondence. So again, make a table. Try to list the elements. So we will try to list the elements and see if we can pair them up one to one. So they both have a natural order, and I've listed them here. And so the number 1 corresponds to the number 2. 2 goes to 4. 3 goes to 6, and so on. 8 goes to 16. And in general, if a natural number is n, it's going to be paired with the even number, which is just 2 times n. Now, this is a one-to-one correspondence between these two sets. So I know the cardinality of the natural numbers equals the cardinality of the even numbers. These are the same size, which is kind of shocking. I hope. It's really very interesting. So it's almost as if you can remove half of the natural numbers and you still do not affect the size. So we can remove all of the odd numbers from the natural numbers, but it still doesn't have any effect on its cardinality. It still has cardinality aleph null. Now, this turns out to be the defining property of an infinite set. This definition is question 5 on homework 10 if you do that assignment. Here is the definition. The set A is infinite provided there exists a one-to-one correspondence between the set A and one of its proper subsets. Well, what is a proper subset? We're going to define it informally. A proper subset is like a sub-collection of the original set. It doesn't have all the same things in it as the original set, but has some of them. So here's a good example, the one we just looked at. The even numbers is a proper subset of the natural numbers. Every number in the set of even numbers is also a natural number, but these are not the same. Now, don't let this confuse you. This is true. They have the same cardinality, but they are not the same set. So this is a property of infinite sets. You can form a one-to-one correspondence with one of its proper subsets. Now, just to give you an example where it doesn't work, if you have a set that's not infinite, there is no way that you are going to form a one-to-one correspondence between that set and one of its proper subsets. So here's an example. A has the numbers in it 1 through 10. So the cardinality of A equals 10. There are 10 numbers in there. B has cardinality 5. B is a proper subset, but we know that the cardinality of A is bigger than B. There is no one-to-one correspondence possible. So this only works for infinite sets. That's the only time you can form this one-to-one correspondence between a set and one of its proper subsets. Okay, so far we have the cardinality of the natural numbers equals aleph null. And the natural question is, are there bigger ones? Is there a set that has greater cardinality than the natural numbers? So before we tackle the rational numbers, let's look at the integers. Do they have the same cardinality? you may remember the Hotel Infinity. We created a table and we showed that this is true. But, sorry, suppose I've never heard of the Hotel Infinity. How can we set this up? We need to list the elements of the natural numbers and the elements of the integers. Now, it's easy. There's an order to the natural numbers. They start at the number 1. The integers, there's no first number. So to come up with a table is a little complicated. So I have a trick to get us started. This is the number line. This represents all the integers. This goes on forever this way, goes on forever this way. And what we're going to do is select them, start in the middle, and select the number 0. And then I'm going to wind around and grab the numbers like this in a circle. So I'm just winding around, collecting the integers, and if I continue this, we would get all the integers. So how does this help? Well, now unwind the rope. And we can start pairing these up. Here's the first one. Here's the second one. Here's the third one. Here's the fourth one. Here's the fifth one. Here's the sixth one. 7, 8. And this tells me how to make my table, which I have done for us here. So again, 1 got paired up with 0. 2 got paired up with 1. 3 got paired up with -1, and so on. Now, this is where it gets a little complicated because we need a formula, but we have to have 2 formulas. So let's see if we can make sense of this. Suppose, let's look at, just pick a number at random, 120. That's a natural number. What integer does it correspond to? Well, this is an even number. So my formula says divide it by 2. Sorry. So 120, we can do that in our head. That corresponds to 60. All right. What about an odd number? Well, I have to use this kind of funny looking formula. This says take that number, subtract 1, and divide it by 2. If you do that, inside the parentheses I get 60. I have a minus sign outside, so I know that 121 corresponds to -60. And this is enough for us to claim that these two sets have the same cardinality. Whoops. Which again is surprising because it looks like that the integers have twice as many numbers, but they don't. They are the same. Now, our book does it a little differently. They have a different formula, but it still works, and maybe you like this better. So how does this formula work? Well, look at the number 6. It corresponds to the number 3, just like in our table, but the formula is different. So the formula says we have to write 6 as 2 times n. Well, 6 is 2 times 3, so n equals 3. So the formula says send 2n to n. So 2 times 3 goes to 3, and that's how you get from 6 to 3. It's a little more complicated to me, but some students like it better. Now, what about the formula for the odd numbers? Well, this says that if you're an odd number, 2n plus 1 goes to negative n. So 7 goes to negative 3, which is the same as our formula. So it tells me I need to write 7 as 2n plus 1. So what is n in this case? Again, n equals 3. And so I already know that 7 should correspond to negative 3. But here you can see I've written 7 as 2n plus 1, and then I have to send it to negative n. So that's how that formula works. So this is optional, whichever one you like best. So use the formula you like best. In our class, you're not going to have to do this for me on a quiz, but sometimes in other semesters, when we don't have a pandemic, you would have to be able to do this. Okay, what are we going to look at next? The rational numbers. So we're going to pause here and I will call the next part, part 2, for the rational numbers.